Our first speaker is Professor Graeme Zosky, and he's the Deputy Director of the Menzies Institute for Medical Research and a Professor of Physiology in the Tasmanian School of Medicine at the University of Tasmania. The aim of his current research program is to understand the determinants of lung health and disease with a particular emphasis on environmental health. He has published more than 100 peer-reviewed scientific articles and has received $8 million of independent funding to support his research. Professor Graeme Zosky the title of his presentation today is Silicosis, New Lessons from an Old Disease. Thank you, Graeme.
Thanks very much. When Pam invited me to talk about this, I was trying to think about what would be of most use. And what I thought I would talk about today is a little bit of history of silicosis, some of what we already know, and with a little bit of emphasis towards the end on the emergence of the sort of what I'll call the new silicosis that we're seeing in the artificial stone benchtop space. So what is silicosis? Well, in short, it's an incurable and potentially fatal lung disease caused by inhalation of silica dust. So there's no treatment for silicosis. Some people are fortunate if they get silicosis, they have a relatively mild form of the disease and have relatively little impairment of their lung function, whereas at the severe end of the spectrum, the only option for some people is lung transplant. That's not a good outcome at that point. And as you all know, it's usually linked to the exposure, or traditionally linked to exposure from cutting naturally occurring silica. So traditionally in mining situations, in quarry workers, in tunnellers, there's a famous silica exposure event that occurs in West Virginia nearly 100 years ago, where several hundred workers died from silicosis as a result of cutting a tunnel with very high concentrations of silica in the stone. And as you would have guessed from the new lessons from the old disease, silicosis is one of the oldest known occupational diseases. And so here's something that was published in the late 1800s about workers sharpening tools with stone wheels and getting silicosis and dying from that silicosis. And so this was reported in the early 1800s, and this is something that was published about 40 years later. So even though they were aware that this was an issue, 40 years later there were still plenty of people dying from silicosis. And one of the interesting things at the time is most of these workers were dying from silicosis and tuberculosis, and we're very fortunate that we don't have much tuberculosis circulating in our community because silica exposure vastly increased the risk of dying from tuberculosis. Okay, so the primary risk factor for silicosis is the dose of silica that you're exposed to. There are some other modifying things that we know of, so exposure to cigarette smoke can also increase the risk of silicosis, pre-existing lung disease. But in general, the primary risk factor for the development of silicosis is the dose of exposure, and that's the combination of both the duration of exposure and the intensity of exposure. I'll show you some numbers here. Hopefully there's not too much information on the page. There's two columns I want you to focus on. On the left-hand side here, we have the estimated cumulative dose of exposure to silica. So at the top, we have people who are exposed to nothing up to around 1 milligram per cubic metre years. What that means is they are exposed to 1 milligram per cubic metre of silica dust in the air for a year. So that could be 1 milligram per cubic metre every day for a year, or it could be 2 milligrams per cubic metre every day for 6 months. So that's the cumulative dose of exposure. And so in this particular study, and I think this is data from the US, they estimated the exposure for a whole range of workers, all the way from almost nothing to incredibly high levels of exposure, and estimated the risk of dying from silicosis. So if you start at the bottom, if you're exposed to nothing, you have no risk. All the way up to here, in these incredibly high exposures, your risk can increase up to 60 times, depending on how much you're exposed to. So there's a very strong dose response curve. So the more you're exposed to, the greater the risk of dying from silicosis. That's all well and good. And one of the questions you might ask, well, how common is silicosis? Because that's an important part of this conversation. This might not be of any consequence if hardly anyone develops silicosis or hardly anyone's actually exposed to these sorts of levels. And unfortunately with silicosis, even though it's a very old disease, we have very little data internationally or nationally on the prevalence of it, how common the disease is. There is a little bit of data published from the US. Here, again, a very busy slide. If you just focus on, here we have year from 2001 to 2010, and this is the absolute number of deaths from silicosis across those years. And what you can see is actually the number of deaths from silicosis is actually relatively low. So at least from 2001 to 2010, there was around 150 to 100 deaths every year, and there was a general trend for a decrease in the number of deaths associated with silicosis. So you would argue that it isn't very common, at least in this environment and in these years. And one of the challenges with understanding this is anything that you do to prevent silicosis takes 20 or 30 years to have an effect, because the mortality or the people dying from silicosis were probably exposed to silica 20 or 30 years before they passed away. So there are some challenges. So what about Australian data? Well, there's very little Australian data, as I've already mentioned. There's some old reports that looked at data from the National Occupational Health and Safety Commission, and in 1993 there were around 20 to 30 new cases of silicosis per year. In 2004 there were 6 claims for silicosis in one of the databases for workers' compensation, and as a result of these low reports, and Pam mentioned this already, when there was a review in 2005, a person with a clinical background stood up and said, the silica issue in medical terms is basically over, is a great success story. Australian industry is free of silicosis by and large. So it's kind of interesting from my point of view about the community psychology around this. This sort of silicosis requires or attention on silicosis requires an extreme event, and then people slowly forget over time, and it seems to re-emerge and re-emerge over the years. And we saw a similar thing with coal workers' black lung in Queensland and New South Wales. So I just want to tell you a little bit about what silicosis is and how it develops, so you get a sort of an understanding of the process. And so we're constantly exposed to particles from the environment. So they could be particles from diesel exhaust cars, they could be particles from bushfires, they could be salt particles from the ocean. And when you inhale those particles, they come into contact with the lining of your lungs. So you inhale the particles, and depending on how big they are, they'll deposit in different parts of your lung. So the very small particles will reach the very periphery of your lung, the larger particles will deposit in your nose. And under normal circumstances, the body is very good at ejecting these particles. Now, the particles in and of themselves aren't dangerous to the human body. If you were inhaling a bacteria or coronavirus, for example, you would want the system to respond and try and get rid of it. But the inhaled particle in and of itself is actually not dangerous, for the most part, to the tissue in the lungs. So there are good systems that the lung has to get the particles out. So the airway is aligned with these little beating hairs that slowly move the particles up, and you either cough them out or swallow them. When the particles come into, unfortunately in the case of silica, for whatever reason, and it varies depending on what kind of particle you inhale, it triggers an inflammatory response in the lung. So it triggers an abnormal response whereby the system says, this is something that's dangerous, I need to do something about it. And one of the problems that you have is there's nothing there to kill. So if you'd inhaled a bacteria, the system would say, that's a problem, I'm going to deal with it, I'm going to release all these things that kill that bacteria. When the silica touches the cells respond in the same way, goes to attack the silica particles, there's actually nothing to attack. So what ends up happening is it attacks the healthy tissue around it. So you have these cells that line the airway that have that sort of response. If you're unlucky, the silica particle will actually penetrate the cells that line the airway and make it to some of the deeper cells and cause further damage. And there are also cells in the lungs that are designed or there to engulf the particles and help get rid of them. So these things are called macrophages. And all of these cells, when you inhale a silica particle, generate an inflammatory response. So they're trying to do something about this invading particle, which unfortunately leads to scar formation. And this is, I'm going to show you a few slides like this, so I'll try to walk you through them. This is a section from a lung from someone that has silicosis. This big lump here is a solid bit of scar tissue. All these little bits around here are these macrophages full of silica particles. So why does that cause a problem? Well, your lung has two functions. One is it needs to inflate and get air in. The other function is it needs to exchange oxygen and carbon dioxide so you can survive. The silicosis response, where you get inflammation, injury and scarring, causes damage to both of those things. So firstly, if you get scar formation, your lung becomes very stiff. So it becomes very difficult to inflate. Also, as the scar forms, Here's a section of normal lung tissue. You can see that the tissue is very thin, so that allows the oxygen and carbon dioxide to exchange. In a silicosis lung, fibrosis is a very similar disease. In the silicosis lung, you can see that these very thin air spaces have become thickened, so it becomes very hard for the oxygen to exchange into your bloodstream. So you have two problems: very hard to inflate the lung, very hard to exchange oxygen, so people with silicosis get short of breath. And quite often they're fine if they're doing regular day-to-day activities, but if they try to walk up a set of stairs or do a bit of exercise, all of a sudden they can't get enough oxygen to fund that. So that's what silicosis is. That's a little bit of history, and that's why silicosis is a problem for the body. What I want to shift to now is talking about the different flavours of silicosis, the different types of silicosis. So there are three broad categories of silicosis. The one that we're probably most familiar with historically is what's known as chronic silicosis. So chronic silicosis has two broad ranges of severity. There's simple silicosis and complicated silicosis, or progressive massive fibrosis, and I'll show you an example of that in a minute. We have acute silicosis. The Hawke's Nest tunnel disaster was an example of acute silicosis and deaths from that. And we have accelerated silicosis, and I'll talk quite a bit about that towards the end. So what are the characteristics of chronic silicosis? Well, the characteristics of chronic silicosis is that it's typically diagnosed 10 to 30 years after first exposure. So this is one of the challenges. So that data that I showed you from the US, those are deaths related to exposure that occurred several decades before. So it often becomes apparent after you leave the workplace, so often in retirement. Simple silicosis is often asymptomatic, so it's often diagnosed relatively late, so you don't have any specific symptoms until you get a bit older. Complicated silicosis or progressive massive fibrosis is a much more severe form of the disease and typically leads to lung transplantation. I'm going to show you a few pictures of images of the lung, and so that you understand them, I just want to quickly show you what a normal lung looks like. So this is an X-ray slice, basically this direction through the lung. And what you can see is these little white structures here. They're the airways and blood vessels. And most of the lung is black. And the reason that the lung is black is because air doesn't absorb X-rays, so there's no signal when you put an X-ray through it. Okay, so that's what a normal lung looks like. That's what a simple silicosis lung looks like. It's a very specific form of simple silicosis. Hopefully what you can see is you have these little bundles of scar tissue all throughout the lung. So that makes the lung stiff, makes it hard to exchange gas. At the extreme end of the disease, you have progressive massive fibrosis, and hopefully you can see in this image, particularly in these upper parts of the lung, you have these really white, solid masses of tissue, and if you cut those on a section and look at them under a microscope, you can basically see that there's no airspace there for gas exchange to occur. So that's what chronic silicosis looks like. So you've got the simple and less severe version, and the very severe version of silicosis. Acute silicosis is probably the rarest form because it's usually associated with a very specific high acute dose event. So I mentioned the Hawke's Nest tunnel disaster previously. So this was a situation where a group of workers were exposed to very high concentrations of silica over a very short period of time, and a lot of them developed this kind of silicosis, which typically progresses very fast and is most often fatal. As I said, it's the rarer form of silicosis. I just want to spend the last part of the talk talking about accelerated silicosis. I'm going to call this new silicosis because this is the kind of silicosis that we're seeing particularly in the engineered stone benchtop industry. So it's often associated with high intensity exposure, so it sits somewhere between chronic silicosis, where you have relatively low level chronic exposure to silica over a really long period of time, and acute silicosis, which is incredibly high intensity exposure over a very short period of time. Accelerated silicosis is somewhere in between. What's different about accelerated silicosis compared to chronic silicosis is it develops relatively fast. So it usually develops within 10 years of exposure. It's associated with an increased risk of disease progression. That is, it typically progresses much faster than chronic silicosis, from that simple form of the disease to the very severe form. And some of you will be aware of this story. This is Anthony White, who worked in that industry and died from silicosis before he could have a lung transplant, and he was 36. So he is much younger than what we typically see in chronic silicosis, where workers are often in retirement, have already finished in the industry and are trying to enjoy the good life. And so one of the interesting things to think about is how this sort of appeared and what we already knew before this became in the public domain, became sort of front and centre in the public domain. So if you look back at the literature, there's actually several reports of this issue, primarily in the international literature, in the past decade. So the first publication reporting silicosis associated specifically with artificial stone benchtops was from Italy in 2010. There was a follow-up study a year later in Spain where they looked at one particular family who all worked in the same industry and found that 50% of them had evidence of silicosis. And there was a subsequent study in Israel showing a similarly high prevalence of silicosis in that industry. So it wasn't an entire surprise that there were cases were going to appear in this industry, although this literature, as you can see, there's not that many reports and was largely buried in the international literature. So what does accelerated silicosis, particularly silicosis associated with artificial stone benchtops, look like? So this is the first publication of a series of cases from Australia. The very first report was 2 years earlier. In this particular study, they tried to get a feel for how common the disease was in the country and what the characteristics of it were. Now, hopefully, you would appreciate, having shown you what a normal lung looks like, that that's not a normal lung. So this is one of the cases of silicosis associated with exposure to dust from artificial stone benchtops, and you can see that there are very few parts of this lung that look normal. So the disease is very severe. And this is a biopsy section from one of these areas, and you can see that there's absolutely no space for gas exchange to occur. So effectively, this lung unit is not functioning as it should, or functioning at all. And so in this particular study, they had 7 cases that they were reviewing, and these are the characteristics of the cases. So the interesting thing to note, as I mentioned before, is that on average, the age is much lower than you would typically see in chronic silicosis, some individuals in their 20s. The duration of exposure is much, much shorter, so usually less than 10 years. And for this particular series, they were in relatively small to medium-sized businesses. Now, this isn't a survey of all of the silicosis cases. This was just opportunistic sampling of clinicians who had cases that they were willing to share data on. The take-home messages being that the disease develops much faster than chronic silicosis, so patients are typically much younger, and the exposure is much shorter. So one of the other interesting features, because this is the accelerated form of disease, is how rapidly it progresses. So this is an X-ray or CT scan from someone who had silicosis related to working in this industry in 2015, and this is the same individual 3 years later. So you can see the disease progresses. So at this point, this individual would have been told to stop working in that industry because they've got a clearly severe disease, and even despite no longer being exposed to silica, you can see that the disease progresses. And this would have been pre-lung transplant. So that's all doom and gloom. One of the things that I'm interested in is trying to understand why this is appearing and why this is the case. And there are going to be other speakers who talk about exposure. And how to control that. My main interest is in what happens at the patient or the biological side, and what is it about these particles that make them so problematic? No problem, I'll be done within 5 minutes, Pam. We know that dose is an issue. Okay? So in the artificial stone benchtop industry, there are some practices that result in workers being exposed to very high doses of silica. One of the issues is we don't really know the scale of the problem. So Pam mentioned some figures around 300 to 500 workers. Because we don't have a standardised health surveillance program in this industry, we really don't know how many cases there are, and we don't know how common it is. But if you just take the Queensland example of 300 to 500 cases of silicosis, that means 10 to 30% of the industry have silicosis, which is huge compared to chronic silicosis, where you're talking about 1 or 2 cases in every 10,000 workers. There are many uncertainties about the nature of this particular risk. We do know that the artificial stone benchtops have an incredibly high level of silica. So some artificial stone benchtops have crystalline silica levels upwards of 85% compared to some other sources of silica. but I'll show you some data in a minute. There's something special about the dust that these stones generate. The stone also contains resins that are used to bind the silica together, but also to create marbling effects and various other aesthetic type things. We don't know the toxicity of that resin. So when you're cutting the stone, you'll not only be putting silica into the air, you'll also be putting resin particles into the air. So it could be that the resins are problematic, we simply don't know. And there are also additives that are put into the mix, which also contains things that we know damage the lungs, such as arsenic and various other things. So I'm just going to put up one last slide. This is a little bit of work out of my lab, and as I mentioned, one of the things that I'm interested in is how different kinds of particles modify the response. Now we know that the stone benchtops have very different levels of silica, have very different levels of resin. So one of the experiments that we ran was we took 5 samples of stone benchtops with different chemical characteristics. We grew some lung cells in a dish and put the particles on the cells. And what we do is we measure that inflammation, the injury, and the scarring response. And what was fascinating to me is, so on this scale, the details don't really matter. Basically, the higher the value, the worse it is. So here we have cells that have no dust on them. Here we have cells that have standard quartz, so the kind of quartz that you would be, or silica that you would be exposed to in people who have chronic silicosis. And here we have our 5 benchtop or artificial stone benchtop samples. And what you can see is how much inflammation or scarring that they generate varies considerably. So some of them, for example, this sample here, actually produces less inflammation or injury than regular quartz. Whereas this one over here produces a much higher response. And one of the things that I'm interested in is, why is that the case? And could we potentially identify the kinds of stone benchtops or the ingredients in stone benchtops that are the most hazardous? That's one of the things that I'm interested in. So this is the very last point before I finish up. So this is kind of a plug. If there's anyone who's here who's working in this industry and would like to talk about collaborating, one of the things that I'd be really interested in doing is getting some real samples and trying to test this and understand what might be causing the greatest risk. Thanks for your attention.